numbers of entry. But we must convert those words into numbers in a very smart fashion. So before we kind of dive into the process, I want to do a few definitions. So what is a vector? So to understand what vectorization is. Vectors are simply objects that have a direction in length in an n-dimensional space. You can think of this as an arrow pointing in a certain direction. So we have a tail, which is usually the origin, and a head, where you have the coordinates going towards. And these vectors signify words, and we're going to explore that in a little bit. Second thing is, what is a matrix? A matrix is simply like a rectangular table. You can think of this as like a spreadsheet where each entry stores some information about a certain word. If you look at this matrix here, we can treat each row as a three-dimensional vector. Entries 1, 2, and 3. Okay, so how do we actually turn words into numbers? There's many ways to do that. Typically, we like to use vectors and matrices. I think the best way to answer this question is through a concrete example. Let's say we're trying to vectorize country names. So we have countries from around the world, and we want to convert them into numbers in a meaningful fashion. So we can draw some sort of relationship between them, right? I want to know if Brazil is closer to China or Mexico or India and so forth. So to start with, we're going to have the country name, a word on the left-hand side, and we're going to set it to a vector on the right-hand side. And you'll notice this is a three-dimensional vector. It has an x, y, and z component. Each component stores some information about the word. Okay, you might be wondering now, what does 15, 8, and 4 mean? Well, I'm going to arbitrarily assign 3 characteristics for the sake of simplicity. The first characteristic is population size. To understand a country, you want to know how many people it has, right? Second is, what is its GDP? How strong is its economy? Third is, where is it located? 5 through 35, or is the 7 continents just scaled? And so you can see we have, like, China has the most population from a scale of 1 to 100. Its GDP is fairly strong. It's in Asia. We have the United States, it's less populated, but has a really, really strong economy, and it's on North America. And so if you notice, what does this look like? It looks like a matrix. It's a table of 3 different dimensions. So we can treat, you remember, each row as a vector. And so the nice thing about 3-dimensional vectors here is we can graph them in a 3D space. So let's do that. So we have these vectors right here, and I'm going to plot them on a 3D graph. And so this is kind of pretty cool, right? So each of these rows correspond to specific coordinates, right? We have, for example, USA, 2315, and then we can graph this on the X, Y, and Z axis. And we can do the same for every single country here. We notice like Pakistan and India are closer together, and Mexico and Brazil, England, USA, Japan are kind of farther to the left. So we can get some sort of relationship from this. Now keep in mind, this is still a 3-dimensional plane. So depending on where you are and you look up, you're going to see a different angle. And so let's look at another POV. So we look at a different POV from a more bird's eye perspective. We see India, China, and USA more to outwards, whereas you see the other ones more inwards. And you can say, well, this kind of explains population or GDP. India, China, USA have much bigger populations than the rest. Okay, but this is still sort of hand-wavy. I'm just looking at a graph and trying to draw the relationship. But let's get this really numerical, because that's the point of vectors. So one way to find the relationship between 2 different points on a graph is using a simple distance formula. We want to figure out the similarities. Now you might be wondering, why is similarity important? Well, if you think of when you search for a new word, you sometimes go to the source, what are its synonyms, right? Like if you want to find what an automobile is, you look for, it's a car, so now you know what it is. So that's kind of what we want to figure out here. Remember, each vector here has different components, x0, y0, 0, z0, and x1, y1, z1. We can plug it into a very simple distance formula, find the distance of the heads from each other. We plug Brazil and Mexico's vectors in. They have a distance of 8, while Brazil and China have a distance of 110.5. And this is pretty intuitive, right? Brazil and Mexico are fairly more similar than Brazil and China. But of course, this is a very arbitrary assignment. What if we want to look at language or culture and all these other nuances? This model isn't capturing that. And it's very time consuming. I have to manually assign 3 different characteristics. I have to actually set, the numbers. And what happens if I want to compare socks to USA, to kittens, and so forth? There's not a lot of connection right there. So what's the solution? The idea is to take this process of vectorization and generalize it. So instead of assigning arbitrary attributes, can we generalize this process of vectorizing words? So the idea is words in similar contexts have similar meanings. This is like the $1 million statement right here. So what does this mean exactly? Let's take the sentences, I took my dog to the vet. Let's take the other sentence, I took my cat to the vet. If we remove cat and dog, we get I took blank to the vet. They both have identical contexts. So the words in blank should be similar, right? You can't say, I took my plane to the vet. That doesn't make sense, right? So dogs and cats are similar because they have similar contexts. Before, we were assigning context to it. Now we're using the nature of the words in relationship to each other in a sentence to grab that context. This is a much easier way to approach this. So let's actually try this out. The goal for today is to look at this sample dictionary. Let's just say this world has only 3 sentences. I enjoy math, I like problems, and I like linear algebra. And let's try to extract these similarities between different words in the dictionary. The first step is to figure out context. To look at context, we take this idea called the window size. We set the window size to 1. What does this mean exactly? We're going to look at one word to the left and one word to the right of a given word. If it's between that, then we say it's similar to each other, or has the same context. So for example, enjoy is next to I, like is next to I twice, enjoy is next to math, and so forth. We can build this table. We can turn this into a co-occurrence matrix. So the word co-occurrence is essentially the word appears in another window size of another word. We treat this as a co-occurrence. And this is how we kind of store context data. So we can kind of build this up. Like occurs next to problems once, like occurs next to I twice, and so forth. But what do you notice about this table? Okay, first, it's a matrix. Each of these rows are vectors. We could technically figure out the similarities between them, but it's a very sparse table. Sparse meaning there's a lot of zeros. The amount of information is spread out. If you're trying to store, think the English language has so many words, so many sentences. It's really hard to store such a big model. So what's the solution to that? Well, there's this idea called singular value decomposition. This is a linear algebra concept. And the goal is to take this really sparse table and condense it down into its most valuable information. I just want to know certain things about words in relationship to other words. We don't need all these zeros. So it's a factorization process. So we take the matrix, which is our original co-occurrence matrix, and we factor into U, sigma, and V transpose components, which I will explain in a little bit. The new co-occurrence matrix we're going to look at is U. So let me explain exactly how this works. Before that, I want to give some definitions again. This is kind of technical, but stay with me here. Transpose simply means swapping rows and columns. So you can think of this as turning the table on its side. And we need to know what eigenvalues are. They explain the variance in data. Then eigenvectors explains the direction in data, direction of the vectors. So the process of factorizing, we first multiply the matrix by its transpose. Then we find the eigenvalues of the result, and we sort them. Now, this is a very important step. The eigenvalues store valuable information. It says each number gives you how much, it explains the variance in the data. And we sort them in descending order. So the first number in the top left is going to tell you the most about a given word's context. If we go down the diagonal, we'll have a number that doesn't really explain a lot, so we may not need it. That's the whole point of this factorization process. Then step 4 is creating a matrix where its singular values are its diagonal. We use the eigenvalues to generate the eigenvector matrix V, and then this product, A, which is step 1 times V times the inverse of the S, we get our new co-occurrence matrix. That was a lot of words, that was a lot of math. I really like to look at things visually. So let's look at the breakdown of what we just did. We took a matrix M, broke it down into its U, sigma, and V transpose components. And so, remember, this sigma holds the eigenvalues. So on the top left side, in the diagonal, that term holds a lot of information. That's a very important term, and we want to keep that. As we go down, here doesn't explain a lot. So why do we need to keep that in our table? So let's truncate it. Let's just chop it off. So we can chop this side off and have a smaller matrix. So this is our U matrix before truncating. And this is our U matrix after truncating. As you can see, it's a lot smaller. We can kind of extend this or shorten it depending on how accurate we want our model to be. What do you notice? Each of these words have, again, 3 dimensions. It's another vector. And now because we have these vectors, we can again draw similarities. But before, what we did is we used the distance formula to figure out the distance between 2 coordinates. Well, that doesn't really utilize the vector's direction and stuff like that. So we want a more robust method of determining the similarity between vectors and ultimately words. The solution there is cosine similarity. So if you guys are familiar with cosine, the smaller the angle, the higher the value. So the closer together the vectors are, we consider this more similar. Remember, in the country name graph, you have 2 countries, similar vectors, they're more similar to each other. And then we have orthogonal vectors where they're 90 degrees. That will give you value of 0, which means there is no correlation between 2 different words. And finally, if you have opposite vectors, opposite words, then there's perfect opposite correlation. So the range is -1 to 1. Okay, so we look back at our co-occurrence matrix that's truncated. We can take a look at like and enjoy. We can take a look at all these words in relation to each other. So like and enjoy are synonyms. So if our model is correct, they should give us a high similarity score, and they do. They give us a value of 1. Figure out the cosine similarity, we take the dot product of the components over the magnitudes. Let's see, like and enjoy, yep, similarity 1. Like and linear aren't really synonyms, so they should have no correlation to each other. This is a very simple model. We could always expand this by introducing more sentences and so forth. But hopefully this kind of gives you an idea of how this works. So where do we go from here? What's the application to this? Well, SVD, co-occurrence matrix, is really big in the field of computational linguistics. It can help us in search queries. And so if we're trying to figure out the next word in like an auto-suggest algorithm in Google, if you want to figure out its synonyms, this is a great tool to use. We call this latent semantic analysis. Latent meaning hidden, semantic meaning meaning. It can find the hidden meanings between words. If you look at the words car and automobile, syntactically, they're 2 very different words, but I mean the meaning is almost identical. You might be wondering, how does this connect to like ChatGPT and other language models today? So ChatGPT is more like deep learning, neural networks. It needs a training data set to work on. This is a lighter tool. So if you're using less complex problems, if you don't want as much computational power used, you want to use something like this. And this kind of helps you break stuff down. Yeah, so hopefully this gives you an idea of how to draw similarities between words. Thank you.